Ken. Can everybody hear me okay? Good. I can actually hear myself, so that's a good sign. Before I start, I have to give a shout out to Ken. We would not be here if it weren't for Ken. I mean, he got this event rolling. He's been shepherding it amazingly for 15 years. His energy, his enthusiasm, his dedication, his compassion, they're just all just beyond the realm. He's just amazing, and this event is amazing because of his keeping it rolling and thriving. So let's give Ken a hand for making this happen. And I have to say, I'm really delighted to be here. This is one of my favorite events, and to be here a third time is really a treat. So I'm going to talk about weather and climate intersecting, and I'm really fortunate in my new position at Weather Underground that I get to write about both weather and climate. If any of you are familiar with the site, there's a section of blogs, and Jeff Masters was one of the founders of Weather Underground, and he's done a blog with them for about 10 years. I'm now a co-blogger with him, so for now you have to go to his blog, and I've got the URL there. And you'll see both his posts and my posts, and our bylines are on the individual posts, but off to the side will be his picture and bio, and we're working on kind of the branding of that. So that's where you'll find my stuff, and I post usually 3 or 4 times a week, and Jeff posts several times a week as well. And there's many, many comments. It's a very engaged community. Any of you who are weather aficionados, you can join Weather Underground. You can hook up your personal weather station to the network of something like 100,000 stations and engage in the dialogue on the blog. So I encourage you to do that. And my Twitter handle's at the bottom. So I'm going to talk, as Ken alluded to, on the intersection of weather and climate in several ways. First of all, I think we'd all agree this is a weather event, right? Does anybody recognize what weather event it was? Or say what year it was? There was a big ice storm in central Nebraska. Does anybody remember that or did experience that? About 10 years ago, yeah. Just amazing. I think we'd all agree this is climate, right? This is a trace, it's a very schematic trace from my book of what we experienced most of the last 100,000 years, ice age conditions. Then it warmed up about between 10 and 15,000 years ago, a few minor oscillations, and now we're surging up ahead of that. This is where we're headed the next 100 years and beyond. Okay, so that's climate, right? That's not tomorrow's weather. What about this? This is a scene from the Dust Bowl in the 1930s near Dalhart, Texas. So obviously there's some very hot, dry weather going on, but is it climate also? Where does the Dust Bowl fall? It only lasted a few years, but it was an epic event. So let's take a look. I'd like to make the first part of the talk a little more than the first half about long-range forecasting. And by that I mean going out beyond 10 days. What can we say now about what might happen in a given community, say a month out or 2 months out, or can we say anything? And then the last part of the talk will be looking at what kind of weather we might expect as the global climate continues to warm. I'll come back to the graphic at the bottom left. It's pretty fascinating. So I want to start out and kind of lay the groundwork by talking about the 2 kinds of forecasts, because that's really important in understanding both weather and climate. So probabilistic forecast you all have experienced, maybe just not thought about it in those terms, but probabilistic just means it's giving you the likelihood or the odds of something happening. So I'm going to go to an analogy I hope works for you all, Nebraska football. These are the calls from late October last year for how the season would end up for various teams. And you can see, for example, Nebraska, a 0.7% chance of the season ending 8-4. Let's see, 8.5% chance they would end up 9-3, and this is not counting postseason. 38% chance of 10-2, and a 52% chance that the season would be 11-1. So I believe you were 9-3, right? Is that correct? Okay, yeah. So this shows you that at this point anyway, this particular prognosticator had said there was only an 8% chance of that. But even an 8% chance of something doesn't mean it's not going to happen. It just means the odds are low, right? So probabilities help you gauge what's most likely, but they don't tell you exactly this will happen. Deterministic forecast, on the other hand, does tell you flatly this is what will happen. It may be right, it may be wrong, but it's a definitive forecast. So again, going to Nebraska football, this ESPN's Mitch Sherman, decided last Christmas or 2 years ago, Nebraska will lose at Wisconsin in overtime, went out to claim a share of the Big Ten West. The Badgers will get the trip to Indianapolis via the tiebreaker as the Huskers celebrate Pelini's 6th 9-win season in 7 years and point to 3 losses by combined 17 points as a sign of progress. Okay, so how did he do? You could tell me better than I can tell you, but it was a 9-win season, I guess. Anyhow, you see what I'm saying about the difference between the types of forecasts. This is flatly saying something's going to happen. The other is probabilistic. So I'm going to now show several different kinds of forecasts that I plucked from the web back on Sunday. And let's think about what kind they are. Are they probabilistic, deterministic, or a mix? This is the Weather Service's worded forecast. How many of you would say probabilistic? You just raise your hands. How many would say deterministic? How many aren't sure or think it's a mix of both? Actually, this one is probabilistic for the most part because pretty much everything is a range. South wind 13 to 16, a chance of drizzle, then a slight chance, a 40% chance, low around 48. It's not saying it will be 48, it'll be somewhere around there. So really, it's all cast in terms of ranges, which makes sense because we never know exactly what's going to happen. Now here's the iconic description of NWS forecast, the same NWS forecast. This is a little bit more of a mix because it's saying the low will be 53, the high will be 60. Now part of that is just stylistic, right? Because especially on a smartphone, there's not as much room to give you a range. So it's kind of an implied range, and this is the case with a lot of forecasts that look like they're deterministic. They're actually probabilities. They're not just showing you the probabilities. They're simply telling you, okay, the high will be 60, but you know and I know that we're saying it'll be maybe in the upper 50s or lower 60s. So here's a Weather Underground depiction of the forecast, and instead of giving actual numbers, or one number for high, one for low, they give temperature trends and precipitation accumulating. So it's a little more detailed. But again, it's kind of a flat forecast. All the probability is kind of tucked in and implied. Everything is numbers, amounts of precipitation, even wind speed. Here's another example. This is from AccuWeather, going out about a week. And again, specific high, specific low, specific amount of rain. Now that's fine as long as you understand, and people I think do get that these are meant to be sort of ranges, but it's just convenient to give us a precise number. Now what about when you go to AccuWeather and you can go all the way out to 28 days? This is the forecast for Thursday, April 30th. It's saying the high is going to be 72, the low will be 52, be 0.36 inches of rain. What do you all think when you see a forecast 28 days out that's that specific, right? You know, can we really make any kind of deterministic forecast that far out? What can we even say about probabilities? I haven't gone in great detail, but I'm guessing these are mostly toward climatology, right? Your average highs by the end of April are probably in the low 70s, average lows are in the low 50s. Obviously, they've thrown in specific rain events, but in fact, here's the averages on the right-hand side. So they have bumped them slightly above average. So on the one hand, you know, a 28-day forecast, it's ridiculous, right? On the other hand, there may be something we can say about whether that far out. Just for the record, here is a study that was done at Penn State University by John Neese. He engaged his students to evaluate the forecast I just showed you, going all the way out 28 days, actually 45 days out, to determine for a number of cities, I believe it's 13 or 15 cities, how did they do? So this is the amount of error in degrees Fahrenheit. As you go up, that's more error. The red line is climatology. So if you simply gave a prediction that the weather will be exactly what the climo average is, how far off would you be likely to be? And it's usually about 7 degrees. And that you can make a climo forecast, you know, a half year from now, and it'll probably still be about 7 degrees off on average. The forecast I just showed by AccuWeather are very skillful in the first few days, but then by about 10 days, they're not any better than climatology. In fact, they're worse. Beyond 10 days, you'd be better off just going with climatology than going at these predicted forecasts. So my point here is not really about AccuWeather. I mean, any organization, whether it's the Weather Service, AccuWeather, if you're trying to give a specific local forecast that far out, it's more likely than not going to bust. Why is that? Probably a lot of you have heard about chaos theory, or as it's often known, the butterfly effect. Ed Lorenz, a very prominent meteorologist based at MIT for many years, he actually visited NCAR for many summers from the 1960s onward. So he made a pioneering insight that this tiny, tiny motions that happen in the atmosphere, way beyond our ability to sense. We have weather stations, official weather stations are maybe 50 to 100 miles apart, where you have mesonets. In many states now, the stations are maybe 5 or 10 miles apart. But there's still a lot of weather that happens between those points. I mean, even if we had a weather station every mile in Lincoln, there's still a lot of weather happening in between. So over time, those tiny motions gradually can propagate, reverberate, build in the climate system in a chaotic way, and lead to big forecast errors, right? Those little things in a few days can feed into big weather changes. And since we can't really detect those little things or move them forward in a forecast model, once you get out to about 10 days, it just becomes kind of random. Now, as I was saying, many of you have probably heard of the butterfly effect, but it was actually the seagull effect before it was the butterfly effect. I just discovered this when preparing this talk. Ed Lorenz wrote something in 1963 where he said one meteorologist remarked that if the theory were correct, one flap of a seagull's wings would be enough to alter the course of the weather forever. The controversy has not yet been settled, but the most recent evidence seems to favor the seagulls. So even then, in 1963, he was aware of what he would eventually call the butterfly effect. So if you're a forecaster, a meteorologist, or anybody hoping to know what the weather's going to do in a month, I mean, this is pretty discouraging news, right? But actually, the hope is not all lost. We can say something about what might be happening a month or 2 months, 3 months from now, but we have to look at it in a slightly different way, more in terms of probabilities over the large scale. And this is what is referred to in the research world as subseasonal to seasonal prediction. So I'm going to go into a couple of examples of that. The reason that we make subseasonal to seasonal prediction is because the atmosphere and the Earth, what we call the Earth system, does have some long-term memory. You have these little tiny variations that propagate and blossom, as I was talking about, but then they run up against some of the things in the system that are larger and more locked in, and it's the interplay between those that determines our weather. Now, some of these you're familiar with. Anyone that's been out on asphalt on a hot summer day, you know that asphalt is radiating out heat. Well, when the ground dries out in a drought, it does the same thing. The heat energy that's coming in from the sun, instead of some of that energy going to evaporate water, it's all going into what's called sensible heat. That means the heat you can sense. If you stand on it or stand over it, that's sensible heat coming up. And you have more sensible heat when the land is dry than when it's wet. So when the landscape is hot and dry, it tends to help perpetuate drought. If the weather conditions are favorable, the temperatures are going to be a little hotter, the air is going to get a little drier, and there's a little bit of a self-perpetuating feedback mechanism there. It doesn't control the whole thing, but it definitely plays a role. The same works in the other direction when you have a snow-packed landscape. When that happens at night, the snow actually allows radiation to leave the surface more readily, and it gets colder. In the daytime, as any of you know, if you've been out walking through snow or whatever, especially an area where there's some snow and some not snow, you notice that it's generally colder above the snow, which makes sense, right? So snow surfaces tend to keep things colder. Hot, dry surfaces tend to allow things to get hotter. And these things can be folded into longer range predictions. Where are the climatology of snowpack? Where is drought expected to persist, and so forth. There's also a lot of memory in the ocean. I'm sure you all have heard of El Nino and La Nina. It's basically, I won't get into great detail, but it's defined by temperatures in the eastern tropical Pacific in this area that's outlined in red here. It's just west of Peru and Ecuador, just south of the United States, but it's a huge area. It's about the size of the US, the core of it is. And El Nino is when the waters there become much warmer than normal. Usually you have trade winds blowing all the way across the Pacific from South America to Indonesia. Sometimes the trade winds weaken and the whole circulation shifts like this. Instead of the usual flow like that, it's kind of reversed. And the thunderstorms that you normally have over here move over here to the central and eastern Pacific. And that has implications all over the globe because the whole atmosphere has to readjust to the different location of that huge amount of thunderstorm and rising motion. So that's El Nino. La Nina is sort of normal but enhanced. It's when you have the trade winds stronger than normal and the convection shifts way over here. So both of those phenomena give us a lot of predictability, especially if we know an El Nino has set in, and especially if it's in the fall. You can state with some confidence that the El Nino will probably persist all the way through the winter. And that, as I'll show you, tells you something about the weather you can expect. It doesn't guarantee anything, but it gives you a good sense. Now, don't be intimidated by this graphic. It's pretty complicated, and you don't need to follow it in any detail. I'm just bringing it up because it's a very interesting new line of research. A guy named Judah Cohen at Atmospheric Environmental Research started this work about 10 years ago at the National Science Foundation, and he's continuing to issue yearly forecasts based on this, and I'll show an example of one. The idea is, and he's been observing this for about 10 years, and it's proven to have some merit, I think. There's less sea ice now in the Arctic Ocean, right? So you get, because of that open water where there used to be ice in the fall, we're getting more snowfall in many years over Siberia in the autumn, right? That helps build up the cold air, as we talked about, and you get high pressure building. That in turn tends to deflect the jet stream and send pulses of energy upward. And this can take days, weeks for the energy to go up into the stratosphere. And then the motions are much more gradual in the stratosphere. Eventually, it can disrupt the polar vortex and essentially break it into two. And by winter, you have the piece of the polar vortex coming over the US, and you have cold winters in the eastern US. Now, this has been happening a fair amount the last few years. This past winter wasn't exactly the same mechanism, but there was a lot of snow in Eurasia, and it was very cold in the east. So here's an example where you can say in October that the eastern US has a good chance of a cold winter and a snowy winter. So that's pretty amazing, I think. And then there's oscillations, and Ken and I decided not to throw up every name of all of these, but they all involve relationships between the ocean and atmosphere in different parts of the world. This is the Pacific Decadal Oscillation, Southern Annular Mode. If you're interested in learning more about these, I encourage you to go to our Weather Maker Patterns Glossary at UCAR. I helped create this, and it's a fun way to look at each of these and understand what it is. I won't get into that because of time today, but all of these are important. I'll just mention briefly the PDO. That changes about every 15 to 20 years. And when the PDO is negative, that tends to mean more La Ninas. When it's positive, more El Ninos. We're switching now into the positive mode. So for the next 10 or 15 years, there's going to be probably more El Ninos, and the globe will be warming more quickly. The pause, as it's been called, of the last 15 years is mainly because of the PDO being negative. It kind of slowed things down. When the PDO becomes positive, it speeds up again, then it'll slow down in about 15 years. So that's a natural up and down laid on top of longer term warming. It's important to recognize that. So anyway, getting back to the seasonal prediction, how do those concepts get translated into something that you could actually use? One of the main ways is by computer models, and we know about the forecast models. Those of you who are weather lovers know about the GFS model or the NAM model, and those go out anywhere from a few days to maybe 10 to 12 days. Again, those are following actual weather systems, so they're not that useful beyond a few days. But this model, called the climate forecast system, actually goes out months ahead and incorporates things like the state of the ocean, state of the land. So it can tell you, for example, this was issued in late March, early April. This is going out for April, May, June, telling you where to expect it to be drier than average and wetter than average. And Nebraska, as so often is the case, is right in the middle. So if you go up to South Dakota, it could be quite dry. If you go to Colorado or Texas, it could be quite wet. We'll see how well this verifies, but the CFS does show some skill, even out several months. Now, along with computer models, we can use a kind of a more old-fashioned technique, and that's just looking at case studies. Like, what can we learn about what might happen based on past experience? So what I'm comparing here, and this is a really good way to show you how not all El Ninos are the same. This is showing you, again, where above or below normal precipitation happens in the wintertime. This is from July to June. So actually, it covers a whole year, but most of this effect is in the winter. So where it's green and blue, it's wetter than normal. The other, yellow and red, are drier than average. But notice the differences between the weak to moderate El Niños and the strong ones. There's a lot more of a heavy wet precipitation signal in California and the Gulf Coast during a strong El Nino, less so when it's weak. And especially, this is weak to moderate. When they're really weak, there's almost no signal in California. So that's one reason why the El Nino, the moderate or actually borderline El Nino we've had the last few months, hasn't really helped California very much. Same thing with La Nina. Weak La Nina actually can be wetter in the plains, but a strong one has a very strong correlation with being dry. How many of you remember the summer of 1988 when Yellowstone caught on fire? That was a strong La Nina. And you can see the drought signal from that event and some other events. Mid-1970s also. So you can get information from this kind of analysis as well. Now, those of you who follow Weather Service products closely, you may recognize some of these. This is a timeline. We're going out starting with watches and warnings, looking at the time frames in which Weather Service forecasts are generated. So 48-hour forecast, the 3 to 7 day. I'll show examples of these in a minute, 6 to 10 and 8 to 14 day outlooks. There's also monthly outlooks and seasonal ones. So as you go out in time, the forecasts become a little more general. They're not so locally specific, but they're still useful. So here's an example of an 8 to 14 day outlook. These are produced every day by NOAA. You can find them on their website. And what it's showing, as you might suspect, is where it's going to be above normal and below normal, or where it's forecast to be. The dashed lines show you climatology, so you have to kind of reconcile the fact that down here, it's climatology says it's going to be on the wet side. It takes a little while to figure out how to read these, so I won't go into great detail, but you get the general idea. Where it's above normal, it doesn't necessarily mean that there's no chance of it being below normal. It's just shifting the odds a little bit. Here's the seasonal forecast, the same idea again. This is going out, believe it or not, this is the seasonal forecast for next April, May, and June of 2016. And the basic pattern they're showing, by this point, once you get out about a year, believe it or not, the climate change signal tends to dominate. So simply showing that there's a good chance it'll be above normal down here. We will see. So not only the Weather Service, but private entities put out seasonal forecasts. WSI, part of the weather company, also does this. And the CDD reference is to cooling degree days. So this is their forecast for this summer. They're calling for it to be relatively cool from the Rockies eastward and relatively warm on west of the Rockies. Kind of consistent with how the whole winter's been. And so what they've done is translate these temperatures into what kind of cooling degree day impacts will have, which affects power use, air conditioning, and so forth. That's a big interest if you're a utility. If you just have a tiny bit of skill in terms of temperature, you can save a lot of money because you're constantly buying and selling sources of energy. And a forecast doesn't have to be tremendously skillful to provide some value. So you may be wondering, how good are these forecasts? It varies. Here's an example. This is the forecast for last winter, December, January, February, which is meteorological winter. On the left side, we're looking at NOAA's outlook that came out in November. Again, warm in the west, cool in the south, consistent with El Nino, and warm in New England. And this is what actually happened. The dark red is where it was record warm. It was the warmest winter on record in all those areas in dark red. The blue is where it was below average. Now, if you go to the second half of the winter, say late February into March, it was the coldest late February, March they've ever had in a lot of New England. But it's not reflected here because December and early January were actually pretty warm. So it kind of balanced out if you throw it across the whole winter. And kind of a fun fact I have to share, Boston's precipitation for the year, I know most of you have heard about the tremendous snow. They had record snow in Boston. Their precipitation is below average for the year. And you might say, why is that? Well, normally they get a few inches of rain every winter month, but they had hardly any rain for several months. It just snowed, right? So it doesn't take a lot of snow to pile up quickly when it's real cold. So in terms of the actual amount of water in the snow, it wasn't really that much more than a usual winter's rain and snow combined. It just happened to be in the form of snow and cold. So here's the WSI forecast. This one was for last winter. And you can see comparing it, let's compare it to the Weather Service forecast. They both had warm in the west. They both had cool in the south. But what about New England? Quite a substantial difference. And I would say WSI was closer to the mark in this part of the country. Also, Judah Cohen's forecast. This is the guy who did the rather complex connection to snow in Siberia in the fall to weather patterns in the winter. And his outfit correctly predicted a cold winter in the east, which verified. And again, the New England, they predicted it to be warm, just like the Weather Service did. So of these three, it was only WSI that had a cold winter for Maine. But so you can see all of these have some skill, that none of them are perfect, but they all tell you something that would be of value, especially if you're in agriculture or energy or so forth. And again, it doesn't have to be perfect. Now, this is a pretty complex graphic, but I'm just showing you the forecast going forward for what's going to happen to El Nino. We've been waiting on this big El Nino. It's been a borderline El Nino for a few months. The computer models are now pretty confident that it's going to be a strong, moderate to strong El Nino by winter. You have to be careful in the spring. That's when the system is most likely to shift. So it's called the spring predictability barrier. We don't know for sure what's going to happen until probably summer, but this skinny line is the chances of having a neutral year. Blue is the odds of La Nina, and red is the odds of El Nino. And you can see in climatology, the odds of having neutral conditions are highest in the summer, and then they go down. The thick bars are what's actually being forecast, and you can see El Nino has about a 60% chance of happening this spring or continuing, and then it really builds up to 70% by the summer. Virtually no chance of a La Nina until late this year into winter, and then only about a 10% chance. So there is still some chance of neutral conditions, about a 30% chance. So I think it's a pretty safe bet that it's either going to be neutral or El Nino by the end of this year. And it's borderline El Nino right now. So these probabilities, they may not help you figure out, when to have your wedding in 3 months, but they are really useful for society in general. How many of you have heard of the hurricane outlooks issued by Bill Gray from Colorado State for about 15 years now? Yep. So how good are those? Well, this is a study that was done a few years back, so it is fairly dated. At this point, Bill Gray and also a firm called Tropical Storm Risk, that's TSR, they were issuing numerical forecasts in December for the coming hurricane season. So that would be as if they'd issued one last December for the coming Atlantic season starting in June. Well, for this period, 92 to 2005, those forecasts were actually less skillful than climatology. In other words, you would have been better off ignoring the forecasts. So wisely, they got rid of those. They now issue just more qualitative statements, but they stopped issuing the numerical forecasts. But once you get to the forecasts that are issued in May and June, there's some skill. This is a measure of skill here. 0 means no skill. And by the way, I know this is confusing probably, we're working our way, the time goes from right to left on this chart. So these are the ones issued in December. We're going forward in time. June forecasts are a little more skillful, and then you can see by August, you can be pretty skillful at telling what's going to happen in the hurricane season over the next couple of months. Now here's something you may not have heard about. We now have seasonal tornado outlooks that are in the development stage. And these are mostly based on what's happening with El Nino and La Nina. This was just released several weeks ago. Here's the URL for the press release, but if you just Google Columbia tornado, it should come up. And the researcher's name is John Allen. What they did was look at a number of years, I believe the last several decades, and looked at what happened during El Nino and La Nina years. Was it stormier? Were there more tornadoes? And also, were there more large hail reports? So it wasn't just tornadoes, it was severe weather in general. And they found the strongest relationship was in this part of the country, Oklahoma, Arkansas, North Texas, Louisiana. During El Nino years, the blue means less likely than usual. During La Nina, the red means more likely. So the one place where there's a really strong connection is the Southern Plains. A little bit of a connection in Nebraska for El Nino. In other words, when there's an El Nino going on, it's a little less likely you'll see severe weather here. When there's a La Nina going on, it's a little more varied. But one thing they found is that the big years and the big events are a lot more likely to happen during La Nina. So you may have severe weather during El Nino, but if it's going to be a biggie, it'll probably be during La Nina. Not to say you can't get an individual strong tornado like we saw in Illinois the other day. So their outlook for this year, March through May, and I believe this applies to that boxed area I was showing you, is 60% chance of normal, but 3 times as big a chance of below as above. So the most likely outcome is a normal year, but still a decent chance it could be below normal. And I don't want you to even try to wrap your brains around this graphic. It's from my friend Victor Gensini, College of DuPage. This is very experimental. It's going to be published later this year. It's called a phase space diagram. And the squiggly lines is actually looking at where the momentum is traveling around the world on the jet stream, which is the ribbon of air a few miles high that runs all the way around the northern hemisphere and gives us our stormy weather and our nice weather. This is using the CFS model I showed you earlier to plot over 3 months where are the big short waves and long waves and the upper level storms going to be. In 2011, the system would have predicted a lot of tornadoes. That's indicated by the lines mostly being over here. And lo and behold, there were almost 1,200 tornadoes. 2013, their action was mostly in this box on the other side of the diagram, where it's less likely to get tornadoes, and we only had 371. So about 3 times as many tornadoes this year than that year. So there is some predictability here, and this isn't really El Nino, La Nina, but it may be influenced by those, but it's looking just at the jet stream from the long-range forecast models. So this is something to watch. I think we're going to see more of this over the next few years, so we'll have a better idea of what kind of tornado season, what kind of hurricane season to expect. I'm just going to check the time. How are we on time? Is it? Oh, there we go. Thanks. Okay, so the last part of the talk is getting into the topic of my book, Climate Change and Weather. One of my favorite sayings, climate is what you expect and weather is what you get. Best source I found for this was the novelist Robert Heinlein, written a few decades ago. This photo came from an amazing event that took place in the Atacama Desert of Chile. This is literally the driest place on Earth outside of the polar regions. If you go, it can't rain or snow much in the poles because it's so cold, but outside of Antarctica, this is the driest land area on the planet, and that's water running through the streets. They had something like a ½ to 1 inch of rain across a chunk of this desert. These are places where it can go a whole year and never rain once. This is, I think, roughly 15 years of rain in a single day. And there was actually devastating flooding, something like 100 people died. So the climate you would expect in this area is it's going to be dry because it was dry yesterday, because it was dry last month, but that doesn't mean that's the weather you'll get. Now here's another example. Does anybody know where this was taken? Yeah, byline gives you a clue. This is in Cambridge, Massachusetts. This is MIT. I call it the Alps of MIT. This is where they were putting the snow this winter that they had to plow off the streets and the parking lots. And those are students standing on top of the snowbound. I wish I could have done that. That would have been so fun. So Marshall Shepard, an eminent climatologist at the University of Georgia, he's also the host of the Weather Geeks program. How many of you have seen Weather Geeks on the Weather Channel? Great show. Nice to see some hands going up. He says climate is your wardrobe and weather is what you wore today. So I really like that analogy too. But what if someone is messing with your wardrobe, right? I think this is a really useful way to think about climate change. We're still going to have ups and downs. We're still going to have cold fronts and warm fronts. But let's say your weather wardrobe is 3 t-shirts and 3 long sleeve shirts. Well, in a couple of decades, it might be shifted a little bit. You might be wearing that t-shirt more and the long sleeve shirt a little less. But you'll still wear both of them at different times. So here's a classic example. This is research done at NCAR in conjunction with the Weather Channel, published several years ago. It's looking at the ratio of the number of record daily highs to record daily lows across the whole country. And in any given year, you're going to have thousands of these, right? But the question is, how many in a given year, and if you average them over the whole decade, are you hitting more record highs or more record lows? Back in the 1950s, they were about even. In the cold decades, 60s and 70s, they were biased toward record lows. But then they've been shifting ever since the 70s toward more and more record highs. So in the 2000s, going from 2000 to 2009, you would get about 2 record highs for every record low. We're maintaining that proportion this decade. It actually was 3 to 1. In the last couple of years, went to the negative side, not surprisingly. Now this year is again off to a big start for record highs. I'll have a video related to this at the very end. It's kind of fun. So just in a nutshell, what are we going to experience globally over the next few decades. A lot of this is things that we're already seeing. It's just extending those trends into the future. And what we're seeing here is two different projections of temperature, right? They're both using the same scale, and this is degrees centigrade. So to get Fahrenheit, you more or less double that. Or, yeah, that's right. So 4 degrees centigrade is about 8 to 9, almost 8 degrees Fahrenheit. So you can see basically all the reds and yellows means it's warming up. And where there's little dots, that means that the computer models that are used in this agree pretty strongly. Where there's a crosshatch right there, the computer models aren't quite sure. So you can see it's pretty widespread agreement on pretty widespread warming. And on the left, I'm sorry? Oh, okay. So on the left is from a low-end projection. This is basically if we stopped running all our engines and had a massive shift, in the next, say, 10 or 20 years to extremely low emissions. So that's very unlikely. This is if we keep doing what we're doing, and we're probably going to end up more toward this side than that side. You see pretty major warming, 5, 7 degrees Celsius. That's about a 10-degree warmer climate in about 70 years than we have now. That would be like Nebraska's climate becoming Oklahoma's climate. So 7 degrees doesn't sound like much if you're talking about a day where we have a 30-degree temperature spread, but if you average over a whole year, it's a big change. But I have to point out that even in a warming planet, it can still get cold. This is the average temperatures around the globe for February of this past year. Okay? Huge warm anomalies all over Eurasia, very warm in most of Africa, Australia, South America, California, roasting obviously, Alaska. Where is the one spot on the globe where it's cold? To me, this is just the most amazing chart, that it can be this cold in one chunk of the globe and this warm everywhere else. And of course, Nebraska is on the borderline between these. In fact, Ken even told me the mile marker on the interstate that separated the cold from the warm this winter. I forget what it was. He can tell you. So precipitation, here again, there's some pretty strong signals, and I'll go to the higher end because it's a little easier to see what's happening there. In a nutshell, it's going to get wetter to the north and drier toward the tropics. So you can see pretty pronounced drying over Mexico, southwest U.S. The models disagree somewhat on whether it'll rain more down there or not. Now, I want to caution, this is actual how much water is falling from the sky, but as we'll see in a few minutes, that's not all there is to drought. But this is just looking at how it changes in rainfall. A lot of places are going to actually see more rain and snow, but it's going to be coming in a different way, as we'll get into. But the main thing to remember is wetter, mostly wetter to the north, mostly drier to the south, and in the U.S. toward the southwest. Now, it may seem like a paradox that it can be both drought and heavy rains can both be increasing. Well, it's because in both cases, when it gets warmer, water tends to evaporate more. So over the oceans, you're putting more water into the air, and over land, you're sucking water out of the ground. So drought is becoming more intense. Now, it's raining more and snowing more on average in many parts of the world, but those are coming in bigger bursts. It's tending to rain and snow harder when it rains, and then you're getting longer, more intense dry periods. And that may be raising the risk of flash floods in some areas. Last year I talked about the incredible floods in Boulder, which were off the charts. I want to talk about an event you probably have heard about in May of 2 years ago. The tornado in Oklahoma City that killed the 3 storm chasers. Tim Samaras, Carl Young, and Tim Sun. You may not know that there was a massive flash flood in the same thunderstorm. That actually took 14 lives. So that was far more deadly than the tornado. But you didn't hear about the flash flood, you heard about the tornadoes. That often happens with flash flooding. It's a quiet event. It's usually a few lives at a time, unlike a tornado, which could take hundreds of lives. So the flash floods are a real threat and something we need to continue to pay attention to. The other big threat is heat waves, and globally this is the big one. 1995 Chicago, 700 people died. We've made a lot of progress in the United States toward heat warning systems, so that's one area where I think we're doing better. But 2010 in Moscow, 10,000 people plus, and in Europe, 50,000 people died. These are buildings that were built for moderate climates. You're having lows in the 70s and highs near 100, and people were just roasting to death. It was really awful. So I'm going to bring this back to the current and the future and what's happening in California, what might happen in Nebraska. And this is a quote I love. In fact, I was trying to come up with a headline along these lines, but Andrew Friedman beat me to it. It's not the heat, it's the, oh, wait, it is the heat. What's he talking about? Well, it's been shown that the drought in California is actually being majorly exacerbated by how hot it is. And I'll show you two graphs to really make this crystal clear. I just pulled these from the web last night. This is how much it rained in California, going back all the way to the 1890s. And this is averaging it from October to March, right? So it's kind of the core of their wet season. So when you go above this line, it's a wet year. Below this line is a dry year. And you can see a lot of variability, right? There's not really much of a trend. These last 4 years have been very dry. But this winter, which is the last dot there, it wasn't as wet or it wasn't as dry as it was last year. There have been many drier years in California's history, right? So why are we hearing so much about the California drought? Well, partially because it's the 4th year in a row of drought. But this graph will tell you. Look at temperature. It is almost off the chart, almost literally off the chart. Some people have said it's breaking the chart. Continuous warm-up over this is the 5th year in a row that was warmer than the previous year. It's mind-boggling. I mean, you just don't see this in climatology. This is almost 2 degrees above the previous warmest winter, which for a whole average over 6 months is amazing. So again, the drought is bad, but not unprecedented. The temperatures are unprecedented in our settlement history there. So what happens is, as we showed in the graphic earlier, when it gets hot during a drought, you're more likely to have bad impacts because that's sucking moisture from the ground. And so the landscape is getting even drier, and that's allowing it to get even hotter. And that's exactly what's happening in California. And here's what's a little bit unsettling. A study just came out in Science Advances, a major journal published by Science. Lead author Benjamin Cook. Unprecedented 21st century drought risk in the American Southwest and the Central Plains, right here. So what they did was they looked at model projections for what's going to happen. This is looking out to the 2050s to the 2090s. So starting in about 35 years and then going out from there. This is looking at the high-end model projections for how much carbon is going to be emitted by fossil fuels. And the high end is really, we're on that track right now. So any reductions we do will reduce this risk. But this is just assuming we're going to continue forward as we have been. These maps show you 3 different ways to look at soil moisture. The first is the Palmer Index, you've probably heard of. This is the model soil moisture at 30 centimeters, so about a foot below the ground. This is at 2 meters, about 6 feet below the ground. And you can see when you go down 6 feet, there's still a fair amount of moisture from Nebraska north into Canada. But at the 1 foot level, chances are it'll be much depleted. The graph here in the Southwest I'll go to first. Again, this is going all the way back to the year 1000 using tree rings. You see a lot of natural variability, lots of drought conditions in the 1000s to 1300s. This is when the Anasazi settlements in the Southwest were abandoned. Again, up and down, up and down. The 1900s to 2000s were pretty wet overall, especially the last 30, 40 years have been on the wet side. Then look what happens over the next 100 years. The risk of severe drought, the moisture balance representation goes way, way, way down. This indicates mega drought possibilities. Mega drought meaning a drought that lasts more than 10 years as a general definition. Now over the Central Plains, it's not as dramatic a drop indicated, and you can see again it's been very wet here over the last several decades. We don't know how things like irrigation are going to affect this. Irrigation has actually made a big difference in the condition of the soil and even the summertime conditions. For example, in Iowa, you're less likely to get really intense daytime summer temperatures than you were a few decades ago because of all the moisture from the corn leaves evapotranspirating, kind of keeping a lid on the intense heat. But summer nights are considerably warmer. So you're kind of crunching the diurnal temperatures. And I think to some extent in eastern Nebraska. Anyway, this isn't meant to scare you. It's just a very concerning study that because of these increased temperatures, not even because of it getting drier or wetter, just because of the higher temperatures pulling the moisture out of the soil, there's going to be some real concerns. And hopefully the Ogallala will be there for us. But but obviously there's concerns about overpumping of groundwater as well. I think the Ogallala in Nebraska is in much better shape than to the southwest. So bottom line, we're going to have the risk of longer, more intense heat waves, not necessarily in every part of the country or the world, but that'll be the overall trend. We'll still have cold waves, but they won't tend to be as sharp or as long. Droughts will be exacerbated by the heat, and the rain and snow will be more chunked in these heavier bursts. And all of these things are being observed now. This isn't just what a model is telling us, this is what we're seeing. Models are consistent with this in trend continuing, but it won't be a straight line. You don't expect global temperature to do this. It's going to be more like this, that wavy change. And there's going to be exceptions, like we saw in the map of what happened this winter. So I'll close with a bit of good news. It's always good to end on an upbeat note. We're used to dealing with uncertainty in the atmosphere, right? What's a classic example? You hear there's a 30% chance of rain tomorrow. Let's say you hear there's an 80% chance. Well, you're probably going to take your umbrella, right? You don't know for sure it's going to rain. You know there's a 20% chance that it might not rain, but you'll probably say, oh, 80% chance, that's a pretty high risk. There was a time when those didn't exist. They were introduced in 1965, but now they're just kind of, we're used to them. So what if we could think of climate change the same way? Instead of being caught in a debate of is it real, is it not, is it going to happen, is it not? It's probabilities, just like forecasts. The odds of certain things are going to continue to increase. It doesn't guarantee a particular outcome in a particular day or year, but we're going to need to be prepared for weather and climate moving in a certain direction. So that's kind of what I'll leave you with on that. Here are a few resources that will tell you more. UCAR has an excellent climate change, global warming Q&A. IPCC is pretty in-depth, but has some great material. Again, if you want to hear climate scientists talking to general audiences, Real Climate is a good source. And climate.gov is excellent as well. And I have a video to show you here at the end. It's just 2 minutes long. Oh, don't forget my book. You get a copy after the talk. So thanks for being here, and I'll jump right to this video. We produced it at UCAR a couple of years ago. And it's basically explaining the trend toward record highs and record lows using a baseball analogy. I already did Nebraska football, so now it's time for the baseball fans.
What do steroids in baseball have in common with climate change?
Well, imagine a baseball player who's been taking steroids. This baseball player steps to the plate and hits a home run. And you ask the question, was that home run due to the steroids? If you look at the number of home runs he hits over a season when he's taking steroids, and compare that to a previous season when he wasn't taking steroids, it is only then that you can figure out that the steroids have made him more able to hit a home run because it's made him stronger, and the chances of him hitting a home run are greater. So by adding just a little bit more to those naturally occurring steroids in the human body, we change the background base state of our systems.
Okay, got it. But a lot of bad things happen when you take steroids, right?
The greenhouse gases that we're adding to the atmosphere from the burning of fossil fuels are the steroids of the climate system. The atmosphere has very small amounts of greenhouse gases that occur naturally. So by adding just a little bit more of those greenhouse gases by the burning of fossil fuels to the air, we change the background state of the climate system. We increase the temperatures just a little bit, but that increase of temperatures is enough to shift the odds toward a much greater chance for extreme heat events and extreme precipitation events.
Normally, you'd expect record lows and record highs to balance out over time. But now we're getting almost 3 record highs for every record low.
So just as a baseball player on steroids can occasionally strike out,
you're out!
Climate system with increased greenhouse gases can still experience record cold temperatures, but the chances of record high temperatures are still much greater.
And that's what steroids in baseball have to do with climate change. To find out more about climate change and extreme weather, check out ucar.edu/atmosnews.
All right, well, thank you very much, and happy to take questions.
Thank you very much. I'm going to bring the microphone over here so that everybody can hear. Thank you.
I was interested in your illustration of the three globes when you were explaining that point of view. I was reading about something called continental winds. Could you explain that to me?
Continental winds, I'm not sure what that might be referring to. Was there any particular aspect of that? Or, yeah, it's not ringing a bell, unfortunately. Sorry.
Do I see more hands? Okay, over here. There we go.
Your graph, which portrayed the cold situation in the east for our country this last year, was very provocative. But I could not grasp what you were suggesting were the basic theories. Is the Siberian snow guy coming up with some data to explain it, or is anybody? I realize you're saying you put on there that we're all trying to untangle it. But
Yes.
what are some of the basic theories about why this did occur?
I'm glad you asked that, because I didn't get a chance to get into one other possibility. Jennifer Francis at Rutgers is pretty well known now for doing some interesting work on basically the jet stream becoming more contorted in the wintertime as a result of loss of Arctic sea ice. And the idea is that open water where there used to be ice allows more heat to go into the atmosphere in the fall and winter. And that can in turn contort the jet stream from its usual patterns. And her analyses with colleagues have shown some of this effect going on, but it's somewhat being debated. There are other researchers, especially at the University of Washington, who argue that what we're seeing is mostly the result of what's going on in the tropical Pacific. So it's a pretty active debate. I encourage you, if you're interested in this, there's a great debate between Jennifer Francis and Kevin Trinberth from NCAR that Chris it's an ongoing, a good scientific debate. I mean, a real one, a legitimate one. The theory I showed involving the snow in Siberia in the fall and all that, that's been going on for about 10 years. And to me, it's pretty convincing. Again, I don't think every climatologist or meteorologist believes that scenario is what's happening, but I think there's some validity to it. This past winter, the polar vortex didn't ever really fracture that much. It's more that it just dipped down across the Northeast. So it may have been something else going on that gave the correct answer, that made the forecast correct. In other words, he might have gotten the right answer for a somewhat different reason. But I guess I'm just trying to say that it's an open question. And there's also just some natural variability. The Earth and atmosphere is a complex system of a lot of parts and pieces. And you can get naturally occurring warm and cold spells that can last several years, seasons to years, just because of the natural workings of the atmosphere and ocean. I mean, that's been happening since time immemorial. The big question is things that were changing to the climate system, like the Arctic ice loss, which is something new. How is that intersecting with the atmosphere's natural variability? And so it's a great research topic, and they will continue to be. Yeah, I'm sure the people in Boston wish they had some warning about what was going to happen. Truly amazing event there.
Here we go.
Is there any correlation between population and climate?
I'm glad you asked that, and I intentionally leave population out of every talk in hopes that someone will ask it, and someone usually does, which makes me feel good, because I think that's a critical piece of the climate change equation. We have more people on Earth, something like double population in my own lifetime, and more people, more use of fuel, more prosperity, more use of fuel, and that fuel doesn't have to be fossil fuel. If you think about places in Bangladesh that have gone from no power to having solar panels on their huts, and they can now do schoolwork through light systems from these solar panels. So I think there can be some leapfrogging. Nevertheless, if you're adding people to the world, you're going to be emitting more carbon in general. So that is the population connection, and it's something that's going to have to be dealt with in terms of understanding how much fuel will have to be conserved to account for whatever population growth we have.
Oh, a couple things here. In the North Pacific, it's been real warm, and the salmon runs are going to be huge this summer in Bristol Bay. And the Iditarod Trail Race from Anchorage to Nome has been moved from Anchorage to Fairbanks because they didn't have any snow in Anchorage. They had to do that a few years ago. So what's happening there? I mean, it's warmer, so the smolt's are surviving in the Pacific, and the krill is more prolific too, so they're going to have big runs, and there's going to be like 50 million salmon in Bristol Bay this year, which is probably going to be a record.
Oh, amazing. Wow.
Okay, the other thing is, what about the Koch brothers and the deniers of the global warming? And what's the position on that? Two things.
Well, first of all, that's very interesting about the salmon in Alaska. I know that fish in California are going through some real struggles, especially the inland fish, because the streams are going to be extremely low flowing. And, there's mandated releases from reservoirs in California for species like Delta smelt that might otherwise go extinct. So that's going to be a real political football. Will they preserve these species, or will they say, well, we can't afford to do that anymore because we need our water? Of course, you can't turn the clock back if a species goes extinct and say, okay, we're having rain now, we can, whoops, they're gone now. So there's a lot of competing demands in California, but that's very interesting about Alaska. Alaska is kind of the poster child for climate change in the long term, I think. The Koch brothers are, of course, well-known multi-zillionaires in Kansas, oil and gas folks, and they have supported a lot of climate skepticism, climate contrarianism, climate denialism activities. They also, interestingly, funded a study based at Berkeley, conducted by Robert Mueller, called the BEST study, and the intent was to show that there are flaws in how we measure global temperature, so that we can't really say that temperatures have warmed up globally in the last century. So they funded this big study. It got a lot of attention from websites like What's Up With That, which is pretty skeptical. Well, it turns out they did this study, and lo and behold, they showed that all the analyses we've looked at, NOAA, NASA, they're all very solid. They agreed right on the money. It's warmed up about 1.5 degrees Fahrenheit over the last century globally. It's not a controversial thing at all anymore. And the projections, it's going to continue warming. It's just the question is how much. And will we have regional things like the Northeast having more cold winters for some amount of time? I wouldn't be at all surprised if the Northeast had a series of cold winters, even as California and the West continue to roast. But things can turn on a dime when it comes to that. But the main message is globally and nationally, on average, we're going to continue to warm up. This was actually one of the warmest winters in U.S. history, despite what happened in New England, because the West was so warm. Yeah, one last.
First, thank you for your talk. I was wondering if you could compare the long-term predictability of the weather, which I think the first half showed was somewhat abysmal, the long-term predictability of weather, versus the long-term predictability of climate.
Good question. Well, the long-term predictability of climate, I guess in both of these, there's more predictability when you're looking at larger scale and less predictability when you drill down. So in terms of long-term predictability of weather features, there is kind of an inherent limit to, like, where will there be a low-pressure center in Kansas? I think when you go out beyond, 2 weeks, you're not going to be able to say with precision which day will that low develop. But you can say there will be a tendency toward low pressure in the western U.S., say a month from now or 2 months from now. And I think that level of predictability will continue to improve. As far as climate models are converging. There are some areas of uncertainty. I think a big one is, will rain or snow actually increase or decrease in the western U.S.? We know that droughts are going to become worse because of the temperature effect, but it may actually rain or snow more. Some of the most recent climate runs indicate northeast Colorado may get some wetter periods, and that's certainly good news where I live. It doesn't necessarily mean droughts won't be intense or even more intense than they have been, because when it's in the middle of a drought, it's just going to evaporate like crazy. So we kind of have to expand our wardrobe for all of these climate and weather possibilities, because we're entering an age of more uncertainty as we go forward, and how these play out. Not so much uncertainty in whether it's going to warm up globally and even continental scale, but what might happen on the local scale.
Bob, as a climate scientist, I get all the time asked the question, well, if we can't forecast the weather for next week, how can we forecast the climate for 100 years from now? There are two different things that you're forecasting. When we say it's going to be, over the next decade, more record highs and record lows, we're not saying which day. We're not saying which hour. I'm aging, and I can tell you that I can see the progression of aging happening. And I can't tell you what I'm going to be like 2 or 3 or 4 years from now. But I'm moving to a house that's all on one level because I'm anticipating somewhere down the line I'm not going to be able to run up and down the stairs like I am. So we ask that question, and we know that it's a one that I'm the most fascinated by. If you can't forecast the weather for my birthday a month from now, how can you forecast the climate for 10 years from now? We're not forecasting individual daily, and when we're forecasting daily weather, It's this atmosphere that's like water. It's like an ocean, all moving and around. And we can get, as Bob said, the trends we can see. We saw this warm spell in March coming. We went from really cold to really warm, and we saw that 2 to 3 weeks ahead of time. But we can't give you the precision. We can just say that during the summer, it's going to continue to get warmer nights. But we're not going to be able to know exactly which night is going to be the warmest and exactly what the temperature is. So it's hard to answer that question. I wanted to jump in because that's the one that I get asked the most often when I'm on radio or by reporters and all that. Why are you even looking at climate when you can't forecast the weather a week from now? They're two different kinds of forecasts. So it's my 2 cents.
Beautifully put. Yes, I agree.
Well, again, we're at a break, and I've put a half-hour break in here to make sure that everybody gets a chance to go out and get some food if you want to the food trucks. This afternoon at 12:30, we're going to look at Pilger, Nebraska, what happened there. I have a poster up, I think, on the second floor lobby, if you haven't been up there yet, that I have of the photographs of the actual twin tornadoes. There were 4 F4 tornadoes that day. And then at 1 o'clock, we'll have the National Weather Service review all of the severe weather of last year that took place in Nebraska. So I'm not sending you home. If you feel you got to go to the spring game, please do so. But otherwise, if you want to hang around, come back in here in 30 minutes when we look at Pilger, Nebraska, and the Nebraska Emergency Management Response. Once again, let's thank Bob for his talk.